lecture, and in particular, I told you what it means to be a weakly coupled interacting theory. That's where you have a free theory, and then the interaction terms, which means anything that's not quadratic in the fields in the Lagrangian, they have to be small relative to the terms that you already have. And so I told you about this classification. I just learned at lunch yesterday this classification of terms in Lagrangians into relevant, irrelevant, and marginal. That's due to Leo Kadanoff, your other lecturer. So I feel a bit sheepish telling you about it while he was there, but I don't think I ballsed it up too much. So in this lecture, we're only going to consider, in this course, and indeed in the next course, we're only going to consider weakly interacting theories, okay? Now, large parts of physics don't fall into that category. And in some sense, some of the most interesting parts of physics aren't described by weakly coupled quantum field theories. They're described by strongly coupled quantum field theories, where the extra terms you add to the Lagrangian are typically of the same order of magnitude as the terms that you start with. And everything we're going to talk about in this course and the next course, that is basically perturbation theory, that goes out the window. So examples of things that are really beautiful in the world that come from strongly interacting theories. There's something called the fractional quantum Hall effect. So what is that? It's a bunch of electrons moving around in a two-dimensional, effectively two-dimensional semiconductor with a large magnetic field. The electrons all have charge +1 in suitable units. But the particles that you get propagating inside this quantum Hall fluid have fractional charge a third or a fifth or a seventh, typically 1 over an odd number, although recently there's been a 1 over a quarter discovered. So what's happening here? And it's not that there's a new fundamental particle in the world that has a charge a seventh of an electron. It's that interesting things happen when particles interact very strongly. And in particular, somehow a single electron fractionates into effectively 7 objects, which all carry 1/7 of the charge. Okay? Another example of beautiful things that can happen, and in some sense it's the opposite. It's what happens in QCD. The theory of QCD is the theory of quarks, but nobody's ever seen a single quark on its own. Again, it's because the theory is strongly coupled, and it insists that these quarks get bound in groups of 3 that live inside protons and neutrons. Or alternatively, a quark and an antiquark, which live inside mesons. Okay, so there's really wonderful phenomena that can happen in strongly interacting quantum field theories, and they're very, very hard to understand analytically. I think perhaps the most wonderful phenomena that we know of, at least mathematically, is something called the ADS-CFT correspondence. So this is a quantum field theory in 3+1 dimensions, exactly the same kind that we're talking about in these lectures. And at strong coupling, it miraculously grows extra dimensions of space-time and is correctly described by a quantum gravity theory living in 10 dimensions. Okay, so when theories are at strong coupling, what you write down on the board is nothing like what the theory is describing. Okay, the type of particles can be different, and in some extreme situations, even the dimension of space can be different from what you think your theory is doing. Okay, so that's all I'm going to say about strongly interacting theories. You may come across them in various other contexts in the next year, but basically our techniques to understand them are extremely limited. Okay. The next thing I want to tell you about is something called the interaction picture. Did Malcolm do the interaction picture? Yeah, so I can just go dead quick on the board. Okay, so this is a useful trick. To deal with small perturbations. In quantum mechanics. So we know that in the Schrödinger picture, it's the states that evolve in time. And just for this little section, I'm going to start putting S and H and I to denote Schrödinger, Heisenberg, and interaction, while operators are time independent. Okay, in the Heisenberg picture, we know that we do the opposite. We put the time dependence all in the operators. And this interaction picture is just a hybrid of the two. What we do is we arbitrarily take our Hamiltonian and split it up into two pieces. The reason it's useful is because one piece we can solve, and the other piece is going to be this small perturbation. Okay, so in the language of quantum field theory, the first piece is just the free field. That's what we've solved already. And this is going to be the extra terms, the interaction pieces. So this H will consist of the terms in the Lagrangian, which are more than quadratic in the fields. Okay, so time dependence of operators is going to be governed by H0. So what that means is that if we didn't have this interaction piece, we'd basically be in the Heisenberg picture. And time dependence of states is governed by H int. Okay, so if we're going from the Schrödinger picture to the interaction picture, it's like we go to the Heisenberg picture, except we just put in the H0s there. We don't include the H int, the extra term. Okay. So this is familiar. You've all seen this. Yeah. So this last equation, in particular, applies to the Hamiltonian. But, of course, H0 commutes with e to the IH0. So the H0 part doesn't change. But this last equation applies to the interaction Hamiltonian. So in particular, so HI so by HI I mean the interaction part of the Hamiltonian in the interaction picture. Yeah.
You mean the first line H end in the time dependence on the state is
No, that's
That's fine.
that's what I mean. That's because if this was in the Heisenberg picture, I would put H here. So what? And then the corresponding state would have no time dependence. So what am I doing? I'm putting all of H apart from H int. So somehow H int is what's left that's governing the time dependency. It's because I'm moving from the Schrodinger picture. Yeah, but perhaps if I'd written the Heisenberg thing here, then we'd have an H int. Okay, so this is how the extra bit that we're perturbing the Hamiltonian by varies in the interaction picture. So I'll just define this to be what I mean by HI. There's a little room for confusion here because you could think this is the full Hamiltonian, but okay, I'm just defining this. So then the Schrodinger equation is, well, in the Schrodinger picture, we know what it is. It's just this. So now let's plug in these definitions into here. Okay, so this is plugging in the state in the Schrodinger picture in terms of the interaction picture. This is just expanding out the Hamiltonian but keeping it in the Schrodinger picture. And this is the Schrodinger picture state in the interaction picture. Okay, now let's do the differentiation here. We're going to get two terms, obviously. The time derivative hits this and the time derivative hits this. But when the time derivative hits this, it pulls down a minus I, which cancels that I there, h0t, sorry, just h0, and that cancels this term here. Okay? So what we're left with is I, let me write this on the other board. So we're left with this equation for the state in the interaction picture. It looks like the Schrodinger equation, except this is in the interaction picture, and this is just the interaction part of the Hamiltonian in the interaction picture. Okay? You get this equation from Malcolm as well? Yeah, good. So now we want to solve it. And we're going to solve it using something called Dyson's formula. Did Malcolm also tell you about Dyson's formula? No? Time-ordered exponentials? No? Okay, good. Something new. So to solve it, we'll firstly just rewrite it a little bit to solve something different. We want the state in the interaction picture at some given time t. This is going to be related to the state at an earlier time by some unitary operator that we'll call u. So what we really want in solving this is to solve for u. What's the time evolution operator acting on states? Okay, but acting on the interaction picture states. And this u satisfies, you know, the obvious relationships that u of t0 is going to be 1, and that u of t1, t2 times u of t2, t3 is u of t1, t3. You know, the usual kind of evolutionary things that I'm not going to write on the board. Okay, plugging this into here, the equation we have to solve for u is the following equation. Okay. So the time derivative is just at hitting the first argument of t comma t0. It's really this that we want to solve for. Okay, you all happy with this?
How do you get from your
I just plugged this. Oh. So this time derivative hits the u of t, but doesn't hit this. Yeah. And then this u is sitting here. Then I stripped off these states side. So now we have an operator equation rather than an equation on states. People happy with this? Okay, so how do we solve equations of this type when u and h are operators, or in sort of simpler language when they're matrices? Okay. If they were just functions, if u and h were just normal functions, and in particular functions that commuted with each other, then we'd know how to solve this. Right? If u and h were functions, we could solve this by u of t, t0. Well, it's just the exponential of suitably integrated hi. Okay? Why is that? If we differentiate this with respect to t, we differentiate this with respect to t, which now sits up here, which just pulls down a factor of hi of t that sits in front, which the factors of I work out, and you just get this equation. Okay? Is that clear? But this isn't the right answer when these guys are matrices, or in this case, when they're operators. And the problem is that these things don't commute amongst each other. And in particular, hi at one time won't commute with hi at a different time. There's no reason that it should. This isn't right. Because it's typically not equal to 0 when t is not equal to t prime. But this, yeah, thanks. Yeah, that's important. Okay. I guess there's something else I should tell you. If this was a matrix or an operator, what would it even mean to exponentiate a matrix? Well, such things are always defined in terms of the Taylor expansion. So what this really means is that it's 1 minus I times this plus a half this squared plus 1 over 3 factorial, this, and so on. Okay, so it just means the Taylor expansion. The problem is that once you get to that squared piece, you've got this squared, but then you've got two h's, and they're typically at different times, and you can't go past each other. Okay, so that's why this doesn't work to solve this equation when these are matrices. So I think it's best if I just tell you what the solution is, and then tell you what everything in the solution means, and then prove that it's the solution. So the correct solution is given by Dyson's formula. Although, like many things in quantum mechanics from back in the day, this was first figured out by Dirac.
I have to ask this obvious question. Then why is it Dyson's formula?
I think the notation is due to Dyson. I think he figured out you could just write a big capital T there. So it's also true that Dyson understood, well, even developed the whole way to apply this to quantum field theory. So this T we've seen before, this stands for time ordering. And what it means is that if I have two operators, or typically more operators, inside brackets on which T is acting, this is defined to be such that, and we've seen it before, we saw it yesterday, such that the later operators go to the left. Yeah. Sorry, so the exponential.
The exponential, that integral, is it a product of integral or just one integral? Because it's type of the means I should have more than one.
Yeah, so you exponentiate this whole bracket, which means that it's 1 plus this bracket plus a half times this bracket squared. So the issue comes when you get to this bracket squared term and the later ones, because then there's two integrals. So you should write it as, maybe I'll just go over this in some detail if there's confusion. Okay, so this.
You've got your conditions there wrong. It's both times T2
Oh, yeah.
T1.
Thanks. Okay, so this means it's 1 minus I So let me write down explicitly what the time ordering does, and then we'll go through and try to understand why. Okay, so hopefully this will answer your question. Good, so what have I done? I've expanded out this guy here. The one we don't have to worry about. This guy we don't have to worry about either. It's just a single operator. Time order it, it's the same operator. Okay? The first time that we have to worry is when we get this bracket squared, because then we have two h's, and if you were to just expand this out, there'd be a particular ordering, which was this bracket times another bracket where you replace the t primes with t double prime, because it's just a dummy variable. Okay? What the t outside says is that we have to reorder this squared term such that all operators at late times are pushed to the left. So that's what we've done here. This is, well, this is the term that you would sort of naively get, but what we're doing is we're keeping this term only when t prime is greater than t. So hopefully that's what these limits should do. You see that t prime is greater than t double prime. You see that, yeah, okay, it's good. So dt double prime only goes up to t prime. So this guy's always less than this guy, and that's why this is to the right. And this term is when it's the other way around, hopefully. So t prime should always be less than t double prime. And it's true. The t double prime starts at t prime and goes up. Okay? So what this t has done is it's just reordered this the operators in this thing with the squared. And you can do the same for the cubic term and the quartic term and every term. Okay? Does that answer your question? Yeah. By the way, you can check. It turns out that these two are actually equal to each other for this quadratic term. So that's a little exercise that I run through in the notes, but you can check. It's an exercise in relabeling dummy variables, basically. Yeah.
Why is it that multiplying that bracket by squaring that bracket produces this double integral?
So it definitely produces a double integral. Right? If there was no t, it would be the integral of t prime t0 to t hi t prime times the integral of t0 to t dt double prime. Right? It's because the integral sits upstairs in the exponent. So you definitely get a double integral.
Okay.
Right? It's this whole bracket squared plus this whole bracket cubed Taylor expansion value. Yeah.
I'll talk about it later.
Yeah.
Sorry.
So if you treat the t thing as an operator, like what you have is, like, you take the exponential of this integral. Like, the integral is well defined. It's an operator. The exponential of the operator is also well defined.
That's right.
So this is like a arbitrary operator somewhere in the space of operators on the Hilbert space, and it probably is not part of that one parameter group. In fact, I'm sure it's not part of that one parameter group of H's. So, like, it.
No, I mean, it's not an exponential.
Yeah.
It's a unitary operator.
So this t thing, like, it's not. Is there any reason to believe that this would, like, you could take some arbitrary operator and apply t to it and get something well defined?
Yeah, there is. I urge you to consider it afterwards. And it's just a Taylor expansion in exactly the same way that the original guy was a Taylor expansion, but with different orderings. We'll talk. Any question about whether an operator is well defined from now on, just ask me afterwards, and we can chat then. Okay. Okay. So let me just prove that this is the case. So the key thing is that this t symbol here means that inside everything commutes. Okay. So inside or under the t sign, everything commutes. So why does everything commute? It's because you can write them any way you want inside here, but this guy is just going to win and reorder them for you. Okay? Yeah.
If you mean that it's the same operator at different times, not different operators.
No, I mean operators are any operator you like at any time you like. They all commute under the t sign, by which I mean that it doesn't matter which order you write from here, because at the end of the day, you've got to go and realize that guy's there, and that's going to dictate the ordering for you.
Does this, if there are more, I think what Nima is saying is that suppose there are two operators, A and B, and they're at different times.
Oh, good. So then I guess this is ambiguous, and you have to worry. You're right. But certainly we've just got a single operator at the moment, so that's not going to be the case for this proof. What this means is that when we take this differentiation, it doesn't matter where we write the thing that we pull down compared to the rest of the integral, because it's all just going to be decided by t anyway. So let me just put it to the right. Sorry, say it again. Do I want to?
Each of the something.
Oh, sorry. Yeah, thank you. No, yeah, that is right. I'm just differentiating, pulling down the h, and now realizing that, if this t wasn't there, it's not that this hi of t sits to the left, it sort of gets buried in between different terms in the Taylor expansion. But as the t's there, it doesn't matter where I write it, because everything commutes under the t side.
This formula, because we are using the case of bosons, when we change it, the sign does not change.
Sorry, I didn't.
What I'm saying is, are you giving the proof just based on the system we are considering as bosons, where if the time ordering does not have a negative sign or ordering?
Yeah, you're right. If we were considering fermions, there are various minor signs that arise in the time ordering. The Hamiltonian, however, is always a bosonic object. And so for this particular proof, it will hold for fermions. Yeah, it's made of two fermions. Okay, but this isn't quite what we wanted. What we wanted was that it was going to be hi times t of this. We wanted that it was hi times u. But it is hi times u because, you see, all these operators here are evaluated at some time t prime, which lies somewhere between t0 and t. But t is always the latest time. And this guy here is evaluated at t, which means that whatever this t object, this capital time ordering does, it's going to take this and move it far to the left. So this is equal to hi of t okay? And this is true because this is the upper limit of this integral. Okay? So the proof's dead easy. All the hard thing is in explaining what this time ordering operation actually means, what the notation means. Okay, is this clear?
I think you lost an
Oh, yeah, thanks. Any questions? So let me sort of fess up. It looks like we've just solved this equation with very little work. We've just introduced this t. In practice, performing the time-ordered exponential integral of some matrix or more generally some operator is extremely difficult. So this is more like a formal solution than a solution that will be useful in practice. Okay? The real power of this comes if this operator is small and we can understand this in terms of this Taylor expansion, where each term in the Taylor expansion is guaranteed to be smaller than the previous terms, and so we can just sort of terminate at some point when we're satisfied. Okay, so the power of this expression really comes from doing perturbation theory, where perturbation theory is now in a Taylor expansion in e to the h. Yeah.
At the end, you see when you target t is larger than t0.
Mm.
So, what if that's not like? Do we not define our operator if that's not the case? Or we have to negative. If I want u.
If so, I yeah, I wanted. Oh, I see. And I wanted this time evolution operator.
If I want my evolution to be backwards.
Yeah, and if I could define this to be only valid for t greater than t0. You see, if it goes the other way, this guy will end up on the right-hand side. And so there's probably a story you can tell about how it goes the other way with it on the right-hand
So here
side.
forever we assume this u.
But yeah, we'll yeah, it's a good point. We'll assume that they're all this u. Okay. Any questions about this? So what we're going to do now is use this to take a first look at scattering. So we're going to pick a particular theory, and the theory I'm going to choose to work with is sometimes called scalar Yukawa theory. So it's going to consist of two fields. One of them is real. And the other is complex. We'll give a mass little m to the particles that we get by quantizing the real field. We'll give a mass capital M to the particles that we get from quantizing complex field. So far it's just two free fields. And now we're going to add a term which makes the particles we get from quantizing psi interact with the particles that we get from quantizing phi. And the term is going to be the following. G And notice that it's, in terms of these classifications that we had yesterday, this is a relevant term. That means that G here has dimensions of the same dimensions as mass. Okay? So if we want to make this small, G has to be smaller than a particular energy scale. But there are energy scales in the game which G can be smaller than. So we'll take this is going to guarantee that we have a weakly interacting theory. Okay, so let's just try and have a look and see what this new term is going to do, just to try and get some feel for it. So this means that a Hamiltonian, well, we have to go to the Hamiltonian formulation. These first four terms, after we convert the Lagrangian to the Hamiltonian, will be what we called H0. So they'll be the free term. And this last one is going to be what we call the interaction Hamiltonian. So H int is G psi star, psi times phi. Okay. It's positive instead of negative because, as always, when you go from a Lagrangian, which is T minus V, to a Hamiltonian, which is roughly T plus V, you get a plus. Okay, so remember what we just saw in Dyson's formula, that if you have a state, the time evolution of that state is given by acting on it with the exponential of this guy here. Okay?
I thought it was HI, not HN, that we used.
Yeah, you're right. It's this guy here in the interaction region.
Oh.
So then you Taylor expand. That means that you have the exponential of h's, really hi, which is 1, if the state doesn't do anything, plus 1 copy of h acting on the state, plus h squared acting on the state, and so on.
Yeah, I think there is a minus if you.
Here? No, this should always be positive. Yeah, there was a minus sign in Lagrangian.
Oh, in the Lagrangian.
Yeah, but this is that.
Yes.
So let's see what kind of things this is going to do if it acts on the state. So the first thing to notice is that this won't conserve particles. So remember that if we write phi is roughly a plus a dagger, this can create and destroy phi particles. And for the purposes of me not saying phi particles for the next 2 lectures, let me just call these guys mesons. When we expand out psi, we have it in terms of b plus c dagger. So this can destroy psi particles, which is what this b does, and create psi dagger particles, which is what c dagger does. And I'm going to call these guys again just for the purposes of this lecture, nucleons. And psi dagger obviously does the opposite. Okay, just to give you some perspective, the actual Yukawa theory is not dissimilar to this. The only difference is that the psi's here have to be fermions instead of bosons. Okay. And this is a meson, or actually the standard model is a Higgs field. It's terms that look like this that sit in the standard model of particles. These are actually fermions. And we'll get to that later. Okay, so one thing to notice is that the number of these guys, the phi particles, is no longer going to be conserved. I mean, you could figure this out explicitly. You could compute the number operator that we have for these guys, basically a dagger a, and see that that doesn't commute with the Hamiltonian in the meticulous new term we have. Similarly, the number of b and the number of c guys won't individually be conserved, but we still do have this conserved quantity, because the Hamiltonian is written as psi star psi, still has the symmetry under changing the phase of psi, and that would insist that the number of b particles minus the number of c particles is still conserved. Okay. And we'll see this coming out explicitly from the calculations that we do. So a first order imperturbation theory you write down this interaction term in terms of the creation and annihilation operators, and there's a whole bunch of terms. Like I guess there's 8 different terms, and among them is a term which looks like C dagger, B dagger, A. Okay, the A comes from this, the B dagger comes from this, and the C dagger comes from this. Yeah. So what does this do? This will, if we have a state on which this acts, this will kill a meson, if there's a meson in the state, and create a nucleon and an antinucleon. So this kills a meson. And creates a psi bar pair. So that means a nucleon and an antinucleon. So if we were to draw pretty pictures, and soon these pretty pictures are going to have mathematical meaning to them, we might draw a pretty picture like this. Yeah. Yeah, C and B commute, yeah. Yeah. They do commute. And sometimes we'll have to worry about what things commute or don't. But at the moment. No, it's B and B diagonal that commute, and C and C diagonal that commute. B's and C's. You know, I'm sort of being a little bit schematic here just to give you a flavour of what happens. We'll do the real calculation by the end of this lecture. So if we were to draw pretty pictures about this, we could consider a phi particle just moving along in time, and this kind of operator acting on a state that includes a phi particle will get rid of the phi particle and create a nucleon and an antinucleon. Okay? So at the moment, just think of this as a pretty picture, but soon it'll have a fancy name of a Feynman diagram. Okay, at second order in perturbation theory, that means when we expand out that evolution operator, which is the exponential to the quadratic piece, so now there's 2 powers of H interaction. Okay, so at second order, there'll be terms like this. This guy is going to kill a nucleon and kill an antinucleon and create a meson. So that takes us from a nucleon and an antinucleon to a meson. But then this guy comes in and it kills the meson and it puts back the nucleon and the antinucleon. Okay? Yeah.
I don't understand why there is only one term each time.
No, there's not.
should have
There's a whole bunch of
8
terms, 8 terms, and I'm just picking out one because I don't want to write all 8. I'm just giving you examples of things that can happen.
Okay.
Are the other terms as interesting?
Yeah, but they'll do things that I think in this case are all basically the same. They'll add a meson and kill a nucleon-antinucleon pair.
But are they all going to look?
Yeah, they're all going to look like this in this case, and they're all going to look like. What have I got to draw in this case?
That's a each marker.
Yeah, exactly. So what does this look like if I was to draw pretty pictures? It looks like a psi and a psi bar coming in, and they annihilate and they form a meson, and then a psi and a psi bar go out again. Okay, so this is supposed to be heuristic to give you an idea of how these interaction terms, which are just a higher order in fields, when you write them in terms of creation and annihilation operators, how they're going to make states evolve. Okay, so again, a few of the key steps here. The first one is that the interaction Hamiltonian becomes the evolution operator, meaning it's e to the interaction Hamiltonian with annoying time ordering things. And you then expand out that e to the interaction Hamiltonian. There's a 1 plus h squared plus h cubed and so on. And each of those terms can do something. So the h leads to these sort of mesons decaying into 2 nucleons. The h squared leads to scattering of 2 mesons, of 2 nucleons and so on. Okay, so this is the general idea that we're now going to flesh out in detail. And the reason I've sort of sketched it on the board is because from now on there'll be lots of other annoying complications in equations, and I just sort of want to flesh out what the key idea is in all these calculations. Okay. Is this clear? Do people, I get the feeling people are a bit baffled by this. Is it because I was just too schematic? Somebody want to ask a question? Have I cowed you with this? No. Yeah.
I guess this is probably come later, but is there any reason why you drew the diagrams like with, there's no reason to know why the legs on the right side wouldn't be flipped on that?
You mean why not the sidebar there and the side there? No reason. We will later attach mathematical meaning to these diagrams. They'll be used for certain mathematical expressions. But for now, they're just 3 pictures to visualize what's happening. Any other questions? Is it clear? People? Let me push on. Perhaps when everything is fleshed out in more precision. Okay. So what we want to do is actually compute the quantum amplitude and then later the probability for these kind of things to happen. Suppose I actually have a state that consists of psi particle and an anti-psi particle, so a nucleon, anti-nucleon. And I throw the two together at some momentum, and I want to know what's the probability that they come out with different momenta. And in particular, what's the probability that they come out with different momenta by first annihilating into a psi part, into a meson, and then being re-emitted? Okay, that's a nice physical question. Alternatively, I could ask the other question. Suppose that I have a meson here sitting in my hand. I want to know the quantum amplitude that it will disappear and turn into a nucleon-anti-nucleon pair. Or better still, I want to know the half-life of this meson. How long is it going to take, on average, before it does that? Okay? So these are the physical questions we're going to now compute. Aaron.
The first thing you asked was, what is the probability that this particle will change in momentum by first turning into this and then turning back into the particle?
Yeah.
So you can't, am I right to say you can't possibly do an experiment to check that?
To know what the intermediate state is. Yeah. No, so in general, you have to sum over all possible intermediate states that give rise to this. Here's where perturbation theory helps. This came from the h² term in expanding out the unitary evolution operator. Now, it's the only kind of process, up to a few permutations, that comes from the h². So any other scattering processes that come from higher order terms, they're going to be suppressed relative to this first term. So anything else you could draw that looks more complicated.
Right. But I'm just wondering, so there's no reason to ascribe any sort of physical reality to any of these pictures?
Let's get back to it.
Yeah.
Okay. So to calculate amplitudes for these processes, so to make progress and actually figure out what the half-life of a meson is before it decays into 2 nucleons, we're going to have to make an assumption. And this is really a key assumption. It's very important for us to make progress, and it's also a little bit dodgy. Okay? Got problems with it. So let me tell you what the assumption is, and then I'll sort of walk you through why it's plausible, but why it's also not quite correct. So the assumption is the following, that the initial and final states look like non-interacting particles. Good. So what I mean, let me write on the board, actually. Yeah. Are there any other questions about things I'm not going to say? So this means that the initial state that I'll call I and the final state sorry, what did I do wrong? Oh, yeah, sorry. I kept viewing that as a minus sign, yeah. Okay, so I mean that you know, I ask this question, I have a meson in my hand, and I want to know the half-life before it decays. So the initial state is the meson sitting in my hand at t minus infinity.
So it's like a one particle, like we then one creation operator.
Exactly, yeah. Yeah, let me take it to be t equals minus infinity. Okay, well, now you can see that this is kind of plausible. You know, t equals minus infinity. For a particle physics experiment, this could be 3 seconds ago, right? And things happen in microseconds. Yeah, exactly. So it seems plausible. You know, I start with a single meson in my hand, and you know, I'm pretty sure that that's got particle number of mesons 1. Now, meson particle number isn't a quantum number of the full Hamiltonian, but it is a quantum number of the free Hamiltonian, so it seems fair. If we think about scattering experiments, we take 2 nucleons, they're very, very far apart in space, we throw them together, at some point they get close to each other, they interact, things can change, other particles come out, and then they fly off again at far infinity. Again, nucleons are well separated, and particle number seems to be a good constant.
They're everywhere, right? So they're not really far off.
Yeah, good. So this is, there's a plausible reason why you might think this is good, but there are several reasons why it's bad. So I'll get. Let me say a few more words, and then we'll come back to that, because I think I'm going to answer your question. Okay. So 2 reasons why this isn't a good assumption. The first reason is that it seems very hard to deal with bound states. For example, suppose that I take an electron and a proton, and I throw them together, and what happens is they form a hydrogen atom and then move off. Now the state at far infinity certainly isn't a state of the free Hamiltonian. It's, you know, you need to include the interactions. Now it turns out that these kind of processes can be captured in the formalism I'm about to tell you. Yeah, let me not say how, but they can be. So much more worrying is the issue, and I think this is what you were raising. And the issue is that in quantum field theory, you're never alone. And it's also true in classical field theory. If you think of an electron moving in the background of a classical field, if the electron moves off on its own to far infinity, it's still sourcing the classical field around it. It can't really escape from the field. Okay? In a quantum field theory language, this turns into the fact that particles, even when they're on their own, are sort of surrounded by a swarm of virtual particle-antiparticle pairs, which is the quantum manifestation of this field. Is this the kind of idea you were getting at? You're never alone. It's kind of complex, isn't it? So what to do about this? Well, this is a dodgy assumption. More correct treatments would deal with this fact that even when a particle is alone, there's a swarm of particle-antiparticle pairs around it. And we get into these beautiful ideas of renormalization applied to quantum field theory. So we're not going to go that deeply in in this course. What we're going to do is derive certain equations, and then when you come to learn renormalization, these equations, suitably interpreted, will continue to hold. Okay? So for now, we're just going to proceed, assuming that the initial states and the final states are eigenstates of the free Hamiltonian, but aware that it's a slightly dodgy assumption. Okay? Are there any questions about this?
Yes. The Fock space of the free Hamiltonian, their position, they're not their momentum items.
They're momentum items. So there's all the same problem that you have in quantum mechanics. So if you wanted really to define a fairly well localized initial state, you could just integrate over them with some Gaussian wave Macedonian momentum. Have two of those. So it's not a new issue.
Why don't we do that?
We could do that. It's going to turn out to be much easier not to have even more integrals hanging around. So we'll just consider two plane wave states with fixed momentum. But the answers we'll get are easily translatable into any language. Other questions? Okay, so let's actually compute something. Actually, first I should give you a definition. I'm not going to write what I've just said on the board. It's all in the notes, so read it and be comfortable with it. So let me just give you a very important definition. So the amplitude to go from the initial state at minus infinity to the final state at plus infinity well, we've seen what this is. You have some initial state. In the interaction picture, it evolves by this unitary operator that we've seen from the time at t minus to the time at t plus, and then we just take the overlap with the final state. So just the usual quantum mechanical amplitude. But now we send this guy to minus infinity and this guy to plus infinity. Okay. This is usually written in the following way. So this operator here going from minus infinity to plus infinity is called S. It's a unitary operator that's called the S matrix. So S for scattering. So a little bit of history for you. In the 1960s, quantum field theory was basically dead. Nobody was working with Lagrangians. Only a few very smart people were working with Lagrangians, but most of the community had sort of abstracted themselves away from Lagrangians and Hamiltonians and were studying analytic properties of this quantity S. It was called the S matrix program. And somehow, the golden age of quantum field theory started in the early 1970s and was really the death of the S matrix program. You probably heard about S matrices from Nima already, though, because he's working on this stuff, so he probably know more than I do now. Okay, let me let's actually compute something in this theory of ours. We're going to compute the amplitude for a meson in the final state to decay into two nucleons. Okay. What's the initial state? Well, it's the vacuum with a single meson created. Okay. This guy here was this relativistic normalization factor that we're going to have to include in all these calculations. What's the final state? Okay, same relativistic normalization factor. I'm going to call the momenta Q1 and Q2 this time. And I create a single nucleon and a single antinucleon with momenta Q1 and Q2. So let's compute the quantum amplitude. We're in time going from minus infinity to plus infinity for the meson to decay into two nucleons. Okay. So what do? Well, we replace S here, which is the unitary operator, with this exponential of the interaction Hamiltonian. Okay. We then expand out the exponential. So what's the first term? The first term is 1, but 1 obviously is going to give us nothing because this state and this state just don't have any overlap. That vanishes. So the term we're going to look at is the next term in that expansion. So it's a 1 plus h int, where h int is the interaction Hamiltonian. So what's h int? This was our interaction Hamiltonian. It's the integral over d4x. Now, the Hamiltonian is really the integral over space, d3x. And the reason there's an integral over time from minus infinity to plus infinity is precisely because it's the S matrix we're interested in, which is unitary evolution from states at minus infinity in time to states at plus infinity in time. Okay? There's a single power of g here. There'll be other terms, but they will all be smaller in g. So when we say g is small, remember it was dimension full, so it's really small compared to the masses. What we mean is that this term is going to be bigger than all the other terms. So we're just going to ignore the other terms here. Is this clear? So let's just go slowly. Let's expand out each of these. So I'll leave these two for now, but I'll expand out the phi. What do I want to call this? Okay. I think I must have missed a term there. Oh, no, sorry, that's right. That's right. Yeah. So what have I done here? I've written the state I in terms of what we have here. So there's the AP dagger, and there's the square root of 2EP. But at the same time, I've expanded out phi. Now, phi has two terms. There's the A term and the A dagger term. If I act on this with the A dagger term, it creates another meson. But then this is just going to give zero overlap with what I have here. You can check that fairly easily. So the only way it gives non-zero overlap is if I just leave the A term here. So was there a question? Yeah, the size would just be, these A's would just move through the size. That's the point.
So we'll have to be a little more careful next step, because we won't be able to neglect that extra term so easily.
You mean next step here in the expansion?
When we deal with side daggers,
We'll see. But I think it's the same. Yeah.
It's probably a stupid question, but why don't we use the interaction Hamiltonian in the interaction picture rather than in the Schrödinger picture?
We are using the interaction Hamiltonian in the interaction picture. Yeah, I claim we are. What do you...
But shouldn't we have e to the minus I h0t? This?
Yeah, I think these guys are living in here.
Well, the time is infinite, so...
Right, so we're integrating over the time here. And the time is appearing here, and this is where I think these... Let me finish the calculation, because I'm not going to figure this out in real time, and then we'll work it out afterwards.
Is k equal to h then?
K. No, K is something we're integrating.
Right, right. But you've just got. Oh,
Okay.
oh, okay.
Oh, is it just my...
Sorry, I was genuinely confused.
Why was the a dagger term 0?
It's not 0, it's there, but it's 0 by the time that this guy comes and hits it, because this state's going to have 2 mesons, and this state's going to have none. So said another way, if there's an a dagger term here, turn it around, pass through all of this, and
Okay.
this as an a going. So let's just clear up what's on the right-hand side there. Okay, where did this come from? This came from moving this AK past here to kill this, but on the way we pick up the delta function between the two. The delta function allows us to do this integral, sets p equal to k, or I guess minus k, p equals to k. So this then vanishes, and this k becomes.
I don't know, but is the sign very important? Because if we use a conventional field operator, we attach a relation and relation. I created the equation operator with the I kx and the dagger with I minus kx. So there.
Don't worry that this is the wrong sign. Remember that the sign flipped when we were, depending whether these are 3 vectors or 4 vectors, right? Because this means k0 x0 minus k of x. So this is the right sign, but you may be misremembering because originally we had it as this. Okay, now we do the same going to the left. We get this. Again, there are terms with C and B, but now you can see very easily that they just move through and we'll kill this, so it's only these that we need to consider. I think that was
Yeah.
It follows through the same way. Okay, now what am I going to do? I'm going to expand out this f here, which f as a ket vector had a c dagger and a b dagger, but when I flip it to become a bra vector, it's got a b and a c that I can pull out, and I'm going to commute them past these guys. They'll kill this, but I'll pick up delta functions for my trouble, blah, blah, blah. Okay? What I'm left with is just this integral, but this integral is just a delta function. By the way, the k's became q's because the b's and c's here were defined to have the q's, and they give me the delta functions, which allowed me to do this integral. Cool. And there's a 2 pi to the 4. Okay, so we computed our first thing in quantum field theory that's actually non-trivial. We have this theory, you have a meson in your hand, and you want to know the half-life of the meson. Well, we haven't quite computed the half-life. We've computed the quantum amplitude and found that it's proportional to this thing, g. Okay? To compute the half-life, there's a little bit more work we have to do, but it's roughly just squaring the quantum amplitude. And then there's a few annoying factors to do with going from relativistic to non-relativistic normalization, but basically the half-life goes as g squared. Okay, that's the decay time. It's the amplitude squared is the probability for decay. Okay, so it's a bit of algebra, but not too bad. So in the next lecture, what we're going to do is develop this machinery much further and find that there's lots of slick techniques we can use to just write down answers like this, and indeed many more complicated processes as well. Okay. So are there any questions about what we've done? Please.
The Q1 and the Q2 at first.
Here?
No, C dagger and B dagger.
No, they should be K, K1 and K2, and we're integrating over them.
So where is Q from?
It's hiding. This F was the square root of 4 EQ1, EQ2, EQ1 dagger, CQ2 dagger. I may have the Q1s and the Q2s mixed up. So this final state was a state of nucleons which have momentum Q1 and Q2 respectively. So I flip this around, these turn into B's and C's, so there's B's and C's here. I try to get them to kill this, because they move past, I pick up delta functions. So Q1 is equal to K1, and Q2 is equal to K2 as a delta function, which allows me to do this. Okay? So this is the probability for a meson with 4 momentum P to decay into nucleons with momentum Q1 and Q2. The delta function is relieving, and it tells us that we haven't violated any of our precious conservation laws. This is just the kinematic delta function that we learn about in special relativity. It tells us that the form momentum of the decay particles has to be equal to the initial form momentum of the original. So we didn't violate energy conservation laws. Any other questions? Okay.
Thanks.